Hello and welcome. In this video, I want to take a look at how we can tell if a vector field is a conservative vector field or not. Okay. Now, by definition, a conservative vector field is a gradient field, right? So to say that capital F is a conservative field is to say that there exists some scalar function little f such that capital F is the gradient of little f. Okay. Now, we're going to talk about two different methods for determining whether any particular vector field is conservative or not. Okay, and in this video, we're going to look at equating the mixed partials, and in the next video, we'll talk about line integrals being path independent. Okay, so let's start with equating the mixed partials. We have seen in a past video that we can tell that a vector field is not conservative if certain partial derivatives are not equal to each other, right? The thing is, if capital F is conservative, that means it is a gradient of something else. And you think about how you create a gradient. The first component is the partial of little f with respect to x, and the second component is the partial of little f with respect to y. Now, Clairaut's theorem says that if there are second partial derivatives that are continuous, then the mixed partials have to be equal. So take the partial with respect to x and then y, or with respect to y and then x, you should get to the same place. So if p is the partial of some little f with respect to x, and q is the partial of the same little f with respect to y, then the partial of p with respect to y should equal the partial of q with respect to x. If it's not, then this is not conservative. If it is, then it might be conservative, and we'll see why we have to say might. Okay. Likewise, in R3, if you've got the vector field being PQR, right? So P would be the partial derivative of f with respect to x, q would be the partial derivative with respect to y, r would be the partial derivative with respect to z, and various mixed partials would have to be equal. So the partial of the first part with respect to y would have to be the partial of the second part with respect to x, or the first with respect to z would have to be the third with respect to x, or the second with respect to z would have to be the third with respect to y, right? So that's what all these things here are. If any one of these is, if they're not equal, then it's not conservative. If they are all equal, this, then you got a chance of it being conservative, and we would have to have a little bit more to be sure. Okay. So here's my two theorems. One of them's in R2 and one of them's in R3. So the theorem in R2 says, if you've got this vector field F, which is P in the x coordinate, Q in the y component, if it is defined on an open, simply connected region D, and the partial of the first part with respect to the second variable is equal to the partial of the second part with respect to the first variable, right? Partial P with respect to y is equal to partial Q with respect to x. Everywhere on that region, then it is a conservative field. So it's not just a matter of checking that these mixed partials are equal, but you have to also make sure that this is defined on an open, simply connected region. Open meaning it doesn't contain any of its boundary points. If it is on a closed, then it's also on an open. You can just throw away the boundary points because you don't care about them, right? Anyway. And in R3, it's a similar thing. If F PQR is defined on an open, simply connected region, and if each of these three things is true, that the partial of p with respect to y equals the partial of q with respect to x, and partial of p with respect to z equals the partial of r with respect to x, and the partial of q with respect to z equals the partial of r with respect to y, everywhere on that open, simply connected region D, then F is a conservative field. Okay, I want to take a moment here just to think about what do I mean by a simply connected region. We talked about it in the plane in a previous video, where a region is simply connected if every loop that's in the region can be shrunk down to a point without ever having to leave the region. So if you have holes in the middle of it, then that's no good. However, in R3, it's a little different. So for instance, picture a solid sphere, solid ball, okay, and take another ball out of the middle. So you've got a gap inside. Editor Will here, between recording this video and editing it, I went in and cooked dinner, and I had to cut open a hamburger bun for my wife. Um, it was, it's a gluten-free bun, and it's not their standard ones anyway. So um, it was very spherical, and I cut it in half, and there was a bubble in the middle. It was mostly hollow, and it's like, I've got a simply connected hamburger bun. Of course, once I cut it, it's not connected anymore. But when it was together, it was simply connected with that big old bubble in the middle. That's exactly what we're talking about here. Is a sphere with another sphere taken out, a bubble in the middle. There we go. Now we'll continue on with the video. All right. If this was, some sort of donut pastry kind of thing, no hole, you could squirt some jelly or something on the inside there, and it would be all donut around the outside and jelly in the middle. But throw the jelly away so you have a hole in there. Is that simply connected? And the answer is yes, it is simply connected, because if you draw any loop that's inside of the sphere but outside of the little hole that you did, so in between, you can deform that loop around the hole down to a point. That is, the hole doesn't get in the way of deforming those loops down into a single point. So that would be simply connected. On the other hand, if you take an actual donut that's got a hole through the middle, the interior of that, you could draw loops around that hole that cannot be deformed without having to pass through that hole. So the donut is not simply connected, but the sphere minus a little sphere is simply connected. Okay, so they're a little stranger than simply connected regions in R3 can kind of have holes in them, but they can't have certain kinds of holes. They essentially can't have handles. Okay. Anyway, let's take a look at a couple of vector fields and see whether we think they're conservative or not. So here's a vector field in R2. The first component is 2x times log y, and the second component is x squared over y plus 1. Is it conservative? Well, if I take the partial of the first part with respect to the second variable, so partial with respect to y here, the 2x is just considered a constant, but you're multiplying by it, so it comes along for the ride, and then the derivative of natural log of y would be 1 over y, so we got 2x over y. Likewise, the partial of the second part with respect to x would just be, again, 2x over y plus 0. So those two are equal to each other. It's got a chance of being conservative. I look at where this thing is defined. I can't divide by 0, so it's not defined along the x-axis. And natural log of y, the input to natural log has to be positive, strictly positive. So this is defined for all xy's that are above the x-axis, so the top half of the plane. That is an open, simply connected region. So these partials are equal to each other, and it's defined on an open, simply connected region. This is a conservative field. And by the way, the potential function is this. Right? We'll do a video on how you calculate these, but it's just a matter of doing anti-partial derivatives of the parts here, getting all the work. All right. Example number 2. Here's one in 3D. The vector field f, the first component is 2xy cubed z, the second component is 3x squared y squared z, and the third component is x squared y cubed plus zy. Is it conservative? Well, let's take a look. One of the things I notice here is that it's defined everywhere. There's nothing that goes wrong. So yeah, it's open. It's defined on the whole space. That's open and simply connected. So let's see. Let's check those partial derivatives. Partial of p some people don't notice the pattern, so I'm going to point it out that the things that have to be equal, I look at p, which is in the x component, in the first component, and I'm going to take the partial with respect to y, which is the second variable. So then I have to do the second component with respect to the first variable, right? So partial p, partial y, partial q, partial x is first component, second variable, second component, first variable. The next one is first component, third variable, so third component, first variable, right? That there's this duality of which component you're doing and what variable you're taking the partial with respect to, and then you just have to do it the other way to see if that's equal. Okay. So the partial of p with respect to y is 6xy squared z, and also the partial of q with respect to x is 6x squared yz, so that's good, those are equal. Partial of p with respect to z, partial of p with respect to z is just 2xy cubed, and the partial of z, partial of, what's this, r with respect to x is 2xy cubed plus 0, so those are equal. And the partial of q with respect to z is 3x squared y squared, and the partial of r with respect to y is 3x squared y squared plus z. Oop, so close, but these are not equal. This is not conservative. Okay. One last example. This is in the plane. There we go. This is y over x squared plus y squared minus, sorry, that's first component, and then minus x over x squared plus y squared in the second component. The question is this conservative? I'll point out that we had this vector space in a previous video. It's actually maybe it's in the other direction, but this was circular motion divided by distance squared from the origin. So there's a question of is it conservative? And it looks at first glance like it's going to be, because if you take the partial derivatives, take the partial, the first one with respect to y and the second one with respect to x, you get the same thing. Both partial derivatives here using the quotient rules give you x squared minus y squared on the top divided by x squared plus y squared all squared on the bottom, and they're equal to each other. Okay? So the mixed partials are equal, but this is not conservative. Right? This is not. There is no potential function. The thing is, the region that this is defined on is the whole plane except the origin, right? You got that x squared plus y squared in the denominator. You can't divide by 0, and the only thing that'll make that denominator 0 is when x and y are both 0. So this is the whole plane except that one little point in the middle, but by taking that one little point in the middle, you've now made it a not simply connected region. It is open, but it's not simply connected. And this is not conservative, and we will prove that it's not conservative in the next video when we talk about line integrals of conservative fields being independent of path. So stay tuned for the next video. Enjoy.